Oi. Você sabe?
Sim, sim.
Quer dizer, eu acho que... Não sei se... Tá certo? Tá gravando? Ok. Okay. All right. So let's start today's lecture, which is the last one before the midterm exam. So today we'll kind of review once again Feynman rules in X space and P space. This time from the operator formalism. Moreover, as we saw, the operator formalism was in Euclidean space. So, and moreover, we will also this time show, actually, it's quite easy to prove the Feynman rules. So, let's start with that. Proof of Feynman rules. So the Green's functions that we were interested in calculating, so we'll start in X space and then we'll move to P space. In Euclidean space, where the nth derivative with respect to j's without factors of I. Remember, in Minkowski space we have an I for each j of the partition function at j equal to 0. And we've seen that there were two forms of the Wick theorem in the path integral formalism. We've used one of them to calculate a little bit some things, but the second one will be more useful for us to prove the Feynman rules. So the second form of the Wick theorem was written in terms of derivative with respect to phi. So we had this exponent of 1/2 dd phi dot delta dot dd phi. And this acted on, well, first of all, we had the phi's from the Green's function path integral. And then we had the potential and source terms. And at the end, we put phi equal to 0. Okay? Now, these Green's functions were also, were specifically the things that were related to transition amplitudes in the free vacuum. And then if we move over to, so this was in Euclidean space. And moving over to Minkowski, this corresponded to time ordering of the corresponding products of phi's. And then with the interaction piece, right? So this was in the free vacuum, but also this meant no division by the same thing without the phi's. this thing, to remind you, this thing was actually z of j. So when if we divided by 1 over z of j in here, then we would get this thing. And then this, via the Feynman theorem, corresponded to the transition in the full vacuum. Which was the Green's function that we were interested in, right? But for that we needed to divide by 1 over z of j, and this 1 over z of j corresponded to vacuum bubbles, diagrammatically, right? So, so this thing here has external phi's at x1 to xn, right? But this without the phi's, therefore, is just vacuum bubbles, no external lines, no external points. And moreover, so I mean, we will see this in detail, but it's kind of obvious, remembering in operator formalism, the same thing will happen in path integral formalism. So obtaining this thing was, via the Feynman theorem, was related to dividing by this 0, which, as I said, corresponded to z. And so dividing by z amounts actually to, okay, at least divide by z in one of the derivatives would amount to considering log z, specifically minus log z, which is defined as w of j. Okay, so this we'll see this in detail, but I just want to get, before we get there, to have a clear picture of all the various ingredients. So, considering minus log z, that is w of j, also known as free energy. Remember the connection to statistical mechanics. Minus log of the partition function is called the free energy. So this one will, considering this one, would amount to dividing by vacuum bubbles, which amounts to the thing we're interested in, the Green's function in the full vacuum with the full Heisenberg fields. All right. Okay. But for the moment, we're looking at this thing, which amounts to this object only, which includes the vacuum bubble. Okay, and for this one, we've seen this Wick theorem, which corresponded to, the second formula of Wick theorem corresponded to this calculation. But there's one more thing which we can observe in here. So the way we derive the second form, we derive the more general formula with f of x and g of x to get from between the first form and second form. But specifically now, when we have this, we note one more thing. We note that if the derivative acts on the phi in here, this is multiplied by j, right? So this is j phi in here. So by this is an exponent. So by acting with dd phi, we get a j down, because it's the derivative of the exponent, j times the exponent, right? Just that oh, sorry, I forgot to say, so this was this was for this piece. So this piece was equal to this. But then at the end we also have j equal to 0. at the end, in order to compute the Green's function, we still need to put j equal to 0. So, for the calculation of the Green's function, at the end, since we put j equal to 0, this will not contribute, right? So the derivatives in here, acting on this term, will not contribute, right? So, might as well, since at the end we will anyway put j equal to 0, we might as well just get rid of this term. This will not contribute, okay? So we say that the result is still equal to five x1 until 5xn minus integral ddx phi equal to 0. And now I don't even need to put j equal to 0 because I already put it. Okay, good. So now we want to calculate. We want to prove the Feynman rule. So let's look at the order n in lambda in the perturbation. So is order lambda today. So this we've denoted by g with an upper index n. And then this is this thing, and now we expand this exponential, which comes with a lambda, up to, so let's moreover consider specifically v is lambda phi to the p of p factorial. Okay, so polynomial potential, which is our the case we're most interested in. And then we look at lambda to the n in the exponential. That is to say, we consider here minus lambda to the n over n factorial from the exponent there. And then n integrations, let's call them y, yn, phi, wait, did I? There's no p factorial in my notation, right? That's annoying because afterwards there is, so. Oh no, I redefined it. Fine. Alright, so let's consider it like this. So phi p y1 until phi p yn. Alright. Yeah, and phi equal to 0 at n, of course. Okay, so first of all, how many phi's there are? So we have little n phi, so let's call this q. This is little n phi's in here, and then p times n from these. So this is the number of phi's. But on it, we act with even number of derivatives. So from this exponent, we'll get 2 times p terms for the pth order part of the exponential. Okay, so actually 2 to the q, let's say. I already used p. So only if this is equal to 2q, so only if this is equal to 2q, we get a non-zero result, right? Because remember, first of all, derivatives, if I have more derivatives than phi's, then I get 0, obviously. But also if I have less derivatives than phi's, I get 0, because at the end I put phi equal to 0. So if I have any phi's remaining, I get 0. So the only non-zero result is when all the derivatives act on all the phi's, right? But here I have a sum. So this is sum over q of this thing, dd phi delta dot dd phi q over q factorial, right? So I have a bunch of terms with different q to choose from, right? But the only one who will give a non-zero result will be the q that satisfies this, right? If it satisfies this, so if capital Q is actually even. If it's not even, it's just 0, right? Okay, so then this Gn will be what? So I have 1 over q factorial coming from this. Then, sorry, I forgot the 1/2, right? So there was 1/2 in here. So I still have then 2 to the q from the q's order term. And then I have q powers of these things. So, well, call them z and w. So integral ddz1 ddw1. So these dots, remember, correspond to integrals. So this is a delta now of z and w. And then this would be a z, this would be a w. Okay? So I have dd phi z1 delta z1 w1 dd phi w1. Right? So that's in detail the exponent. And now I have q of these. So let's say until dd zq dd wq. And then dd phi of zq delta zq wq dd phi wq. So this is the exponent, and now acting on this thing with little m phi's, and then p times n phi's from the other term. So minus lambda over n over n factorial integral dd y1 dd yn phi p y1 phi p yn, then phi equal to 0. All right, good. Okay, so we have these factors, and then they will act on a bunch of phi's chosen from these guys and these guys, right? So let's call the two, what do I call them? Yeah, x and z. No, that's not a good choice. X and y. Yeah. So, okay, here I have x1, xn, and y1, y capital N, but I will call them x and y, even if they might be the same, or just x is just y's, or whatever. So anyway, so I have a term like this, dd phi of z, call them generically z, delta of zw dd phi of w acting on this, right? So the result of this is what we call the contraction, right? The result of this is to contract the two phi's. Phi of x, phi of y, this, which meant really, because you see, from this we get this acts here and replaces x with z. I mean, they're still integral. That's the better way of saying it. And then this acting on here gives a delta, but then integrated over replaces z with x. And then this, the same thing, gives a delta of w minus y, but then integrated over replaces w with y. So we get this, which is delta of x and y, right? But moreover, when we do this, I can choose to act with this here or here. So, and then the next one has only one here. So this also gives a factor of 2, right? That means that, so I have a factor of 1/2 for each of these, but then I get the 2, so then the 2's cancel. So I get a total factor of 2 to the q cancels 1 of 2 to the q, right? So let's say it like this. Okay? And also, there's 1 over q factorial, but that also cancels the term because I have q of these factors. I mean, here I have different z's, but they're all integrated over. They're dummy variables, so it doesn't matter which one of these factors, which one of these whole terms I choose, right? So all of these, I mean, this whole thing will act on 2 phi's, but this or this or this acting gives the same result. So I also get a factor of q factorial that comes from choosing one of these guys. And this cancels 1 over q factorial. So again, let's say this and this, right? Okay. Then what we're left with, so in here I assumed I choose an x and a y out of these phi's in here. But now, choosing one of these x and the y's amounts to writing the diagram, right? So, choosing an x and a y amounts to choosing a diagram. But a diagram in the unsimplified version, the version that we discussed last time, not the one from before, right? However, like we know from before, from the operator formalism, there's a bunch of diagrams that give the same result, right? And the result of this is the symmetry factor. So several diagrams, same result. So what we call the symmetry factor results. Okay. So this is also called statistical weight factor. Okay. And like we discussed in the operator formalism, the way to think about it is to redefine lambda as lambda p over p factorial. And then the number of identical diagrams is almost it almost cancels this factor. So the number of identical final diagrams almost cancels factors up to this S, which was defined as symmetry factor, or now called also statistical weight factor. And so this S amounted to, so here we have minus lambda to the n, but I redefine lambda as lambda p over p factorial, so I have a p factorial of, to the n, and I also have this n factorial, right? So all in all, S is defined as n factorial and is p factorial to the n, which are the remaining factors coming, the remaining numbers coming from here. These numbers were cancelled, so the remaining numbers come from here, divided by the number of equivalent diagrams. Okay. So we can write a simplified version of Feynman diagrams where we only write inequivalent diagrams. And we add the symmetry factor S. Okay, this is what we did in the operator formula, so you're familiar with that already. All right, so I don't think I'll need this anymore, so let me just erase it. So now, let's understand a little bit more this symmetry factor or statistical weight factor. We had examples before, but now I want to make some more observations. So the first observation I want to make is that for any tree diagram, S3 is 1. Symmetry factor is 1. So tree diagram means there are no loops. So tree refers to branchings, right? But no loops means I never come back to rejoin another branch, right? So to understand this, let's take an example. Let's say 5 to the 4. And let's draw some tree diagram. any tree diagram. And something like this, right? So all of these are external points now. Right, so that's a tree diagram. I never come back, with a branch back to another branch to make a loop, right? And you already look at it, you realize there's no symmetry, right? Because remember, the external points are fixed. And because of the fact that I don't come back to the original branch, right? By fixing the external point, I fix anything that comes from it, right? So I fix this, that means I fix this. This falls from this. Then I fix this, also coming from this, and so on. So all of the points and lines are fixed just by the fact that I fix the external points, right? But so that was just to show, diagrammatically, I mean, in a picture, that there's no symmetry. But then I can also do an algebraic proof, remembering that the symmetry factor is n factorial p factorial to the n divided by the number of diagrams. So how would I write the symmetry factor? The number of equivalent diagrams. Right? Well, so in here, I would have these internal vertices and these number of internal vertices is called by definition n, right? That was our definition of nth order Feynman diagram. Okay? But remember, while these things are fixed, so this is x1, x2, x3, x4, and so on. x4, x little n. So these are fixed, but these other ones are integrated over, right? So I put them here on the diagram, but then when I define how I call them, I have n factorial ways of labeling them. Right? But then, for each one of these, I remember what I do. So when I draw the diagram, as you remember, I first write these external points with a line sticking out of them, and then I write these internal points. And now, again, I have p factorial ways of connecting. So when I make connection, let's say, with this one, from this one, I have n ways, then, p ways, then I pick a next one to connect with some other external line or with another external point, with another internal point, p minus 1, and so on until 1. So I get p factorial ways in the end of fixing things, right? So remember that the point is there's a unique way to draw this diagram. I have to, there's no symmetry in it, right? So let's say this is connected to this, and then this to this, and this to this, and so on. So all of this is fixed, which means at each point I'll have a p factorial at each vertex, which comes from choosing which of the lines I use to connect with something else. So the first one I have P, the second one P minus 1, and so on until 1. So all in all, this gives S is n factorial P factorial to the n, divide by the same n factorial P factorial to the n. That's 1. So for trees, S3 is equal to 1. Okay. Let's do some more examples where again I want to verify this rule that the number of symmetries of the Feynman diagram is equal to this factor, n factorial P factorial to n over number of equivalent diagrams. So let's do a bunch of examples. So the figure 8, let's consider the figure 8. So we already considered that before, but so one symmetry comes from exchanging these two lines, then another symmetry comes from exchanging these two lines, like this, and then finally exchanging the two loops between each other. So this is symmetry factor of 8. But let's see if this is also equal to this. So here I have n equal to 1, a single vertex, right? So I have S is 1 factorial, 4 factorial, because we're in phi 4, the number of diagrams, equivalent diagrams. Okay. So how do I draw this diagram? So first I do what I said. I write the vertex, the internal vertex with the legs sticking out, and now I need to connect them. So here I connect them 2 by 2. So the first thing to do is to connect two of these things. Well, this amounts to picking 2 lines out of 4, right? So this is picking 2 lines out of 4, but without caring which is which. So in this way I get 3, right? Because I can choose, let's say, this pair or this pair. How should I say? Well, yeah, well, let me do it like this. So I can choose this pair, but by doing I also choose the lower pair. So this is only one possible choice. This is the other possible choice, because if I choose this, I also choose this. So that's the 1 factor of 1/2, because I divide the two choices. This one and this one are the same. And then finally, this is the third choice, right? So I can choose this in 3 different ways, and then the remaining one is fixed as well. So the number of equivalent diagrams is 3 in this case. So this is 4 times 3 times 2 over 3. This is the 8 that we got from here. Okay. Another example would be this this diagram, also a simple one. So this one has only one of these loops, so just a factor of 2. Symmetry factor is 2. And then the symmetry factor again would be n equal to 1, so 1 factorial, 4 factorial, the number of inequivalent diagrams. But now, remember the external points are fixed. Okay? So, the first choice I have is to decide which of these legs I connect with x1. That comes in 4 possible ways. And the next choice is which legs to connect with x2. That comes in 3 possible ways. And finally, the last two I just connect. So this is 4 factorial, which is 4 times 3 times 2, or 4 times 3. So it is 2. Right? And let's do one more. The setting sun. Again, an example which we did. So the symmetries come from permuting these 3 lines among themselves. So S is 3 factorial for the permutation of these 3 lines among themselves. But S is also equal to n factorial. Now we have 2 vertices. So 2 factorial. And for each I have 4 factorial of a number of equivalent diagrams. Okay? So when drawing, now I choose, I have to connect this one with one of these 2. So first of all, I have a choice of which vertex I pick, right? So that's a 2. Then, once I pick a vertex, I have a choice of 4, which of the lines to connect, right? And now, I have to connect x2 with one of the lines of the other point. So I have 4 choices to connect x2 with one of these things, right? And now, now I have, let me see. So now I have to pick to connect one of these 3 lines here with these 3 lines here. So the first one amounts to so I can pick, I have to choose one of these 3 lines to connect them with one of the others, right? So I get a factor of 3. Then I can pick another one of these 2 lines to connect with another. And finally, the last one is independent. So this is in total a factor of 3 factorial. So this is 2 times 4 factorial times 4 times 3 factorial. Yeah. And then here 2 times 4 times 4 times 3 factorial. So this cancels with this. 2 with 2, 4 with 4. So this is 3 factorial. Okay, so you can play this game further and convince yourself again that the formula we wrote is correct, that the number of symmetries of the diagram is equal to this overall number that we have divided by the number of equivalent diagrams. All right. So now let's consider the final rules in momentum space. So again, we started doing these things, so we already know, but we do them again to understand better with the extra new ingredient that we are in Euclidean space. So we saw that, first of all, we could consider a G tilde that was simply the Fourier transform of the momentum space 1. So dg x1 dg xn e to the I p1 x1 plus pn xn g of x1 xn, the Fourier transform. But we also saw that because of translational invariance, we could isolate the dependence on, say, x1, shift everything, and then we get the integral of the exponent of this ix1 times the sum of momenta, giving us the momentum conservation delta function. So we get this 2 pi to the d delta d p1 plus pn, and then a momentum function, a momentum space Green's function that has this conservation already taken out. So in order to understand a little bit better, let me do the example of just a 2-point function, to propagate. So delta of x minus y is written as integral dp e to the ip x minus y with p squared plus m squared, right? Now, so as we see, there's already the translation invariance that is dependent only on x minus y in this way, right? So if we would do the Fourier transform, we will obtain 2 pi d times the delta p1 plus p2. Well, actually, let's do this already. Yeah, let me do this already like this. Better logic. So I define G tilde of P1, P2 as integral over x and y e to the I P1x plus P2y, the delta x minus y. This will be, for the free theory, this is the propagated delta of x and y. Right, so I take the Fourier transform as this thing. And so This is integral ddx ddy to the I d1x plus d2y. And then this is integral dd p 2 pi d to the I p x minus y p squared plus m squared. Right? And now you can make the integral over, say, y. Yeah, let's say y. Let's do the integral over y. So we write this as p1 x minus y plus y p2 p1 plus p2, right? So p1 x minus y is the same form as this one. And then I have left with the integral over y. So this would be e to the I. All right. So I have integral d dy e to the I y p1 plus p2. So that gives 2 pi d delta d p1 plus p2. And I should have, yeah, and I should have shifted this. So x minus y, call it x tilde. Right, so now I'm left with integral d dx tilde e to the I x tilde wait, I'm doing something wrong, did I? No, it's fine. Yeah. X tilde p plus q1. I did something wrong with signs, I guess. I think I should have put here with minus, because this is the inverse Fourier transform, and this is the Fourier transform. So it should have been like this, I guess. And then p1 minus p. I think now it's better. Right? And I still have integral dd p 2 pi d. Right? And now this thing yeah. Well, seem to be doing this different than in my notes, but never mind. The point is, I'm doing now this integral gives 2 pi d delta d is p1 minus p. So cancel this, and then this replaces this with P1. And in the end, I get 2 pi d delta d P1 plus P2 1 over P1 squared plus m squared, right? And so we see the form that I described for you, that this g tilde is 2 pi to the d delta d P1 plus P2, and then this thing is now g of p, g of P1, right? And I can also call it, because in here in the general form I called it g of, with all the variables, all the momenta, so I could call it P1 and minus P1, right? Because P2 is equal to minus P1. Okay? So g of P1, which can also be understood as g of P1 and minus P1. All right? Good. But now let's come back to the issue that we wanted to describe. So we wanted to describe the Feynman rules in momentum space. So the first observation was that then, if I consider these Feynman rules in momentum space, so the Fourier transform of this propagator corresponds to this propagator. I mean, that was kind of obvious from the form that we wrote initially. This was an explicit Fourier transform in terms of the propagator. So delta of p is now 1 over p squared plus m squared. Okay? But then there was one more point which we made. We said that if we put external points x then this was, by our definition, e to the ipx, and this was, by definition, e to the minus I py. This we defined as external lines. And one usefulness of this, so as I said, this at some level is a notion of definition, whether or not you put these external points in here. But the usefulness of them is if you want to consider these endpoint functions, but with wave functions for external lines, then you see that these things are the simplest kind of wave functions you can put, e to the ipx. So this is the simplest wave function if you want. So there would be two ways of writing them. So one is if I write these external points, then I put this wave function with e to the ipx. But then this thing amounts to not putting an external point with x and y, right? So not putting external point amounts to writing g tilde or g, but we will generally consider g the delta function taken out anyway. Right? The other thing is that we will see, so somebody knew, I remember a question from the beginning of the class, somebody from the beginning of the course, somebody knew about the fact that sometimes there's something called amputated diagrams. So amputated diagrams will appear later on. There would be things related to the S matrix, so physical scatterings of particles. And amputation amounts to removing external propagators. So there are no external propagators in this case. Because note, so if I have a diagram, let's say I have this diagram in X space, right? Now, if I write this diagram in momentum space, there's two ways I could write it. I could still put momenta in here, right? So if I write it like this, this is a diagram for G of P, right? I said that generically we're not using G tilde, but in G. So this would be a diagram for G of P, but with the external points included, with e to ipx times e to the minus ipy included as wave functions. And the usefulness of this comes when you think about, if I don't put this, so if I write this thing, so this is without, right? But now I have a problem, because this, if I look at this diagram, this looks kind of like a disamputated diagram. But this thing, if I consider it as a diagram for the Green's function, this still contains delta of P on both sides. Contains delta of P here and delta of P here, right? Whereas the amputated diagram would contain only this term, no delta of P, neither here nor here. You see? So that's why it's sometimes useful to write, if you write diagrams for the Green's functions, for correlation functions, it's useful to explicitly put the external points and these factors, these external lines, just to remember that there are these external propagators. They're there. It's not an amputated diagram. But either way, in principle, we could have this or this, depending on whether I put the external point. Okay? All right. So now, if I want to write down the Feynman rules. There's one more thing that I want to do in momentum space with respect to the case that we did in operator formalism. So there's one more simplification rather. So in principle, if I have, I don't know, a diagram like this, let's say, the simplest way would be to write momenta, so that's what we did before, to write independent momenta for each internal line. So let's say before, independent momenta for each internal line. But now, a different way of doing it, which is more useful, amounts to considering independent number of loop momenta. That means independent number of loops, which can be thought of as the number, the irreducible number of integrations. So we can, whenever we did it like this, we could use some of the delta functions to write some, to get rid of some integrals. But now, by writing the number of loops, we write directly the irreducible number of integrals. In this case, how many loops do you think there are? How many?
3.
No, there are 3 internal lines, right? As I said, we have to reduce them. There are 2, right? There are this and this. The third, you're thinking of this, but this is not independent loop. It's the composition of these 2 loops, right? So if you call this L1, L2, L3, then I have that L3 is L2 composed with L1, right? So it's not independent. All right. So the number of loops is the number of irreducible number of integrations. That means after I use the delta functions, after using momentum conservation delta functions. Right? All right, so let's do some algebra with these numbers. So let's call V the number of vertices, I number of internal lines, E number of external lines, L number of loops, and yeah, that's it. Okay? All right, so first let's see how many loops there are. Well, so before, for each internal line, we wrote an independent momentum P, right? So we start with that, E, a number of initial integrations. But then, each vertex, remember, came with a momentum conservation delta function. Right? Each vertex came with a momentum conservation delta function, which is a constraint because each vertex is related to internal lines. I mean, it might be connected with external lines as well, but it's certainly connected with internal lines. So that's a constraint on the number of integrations. So we have to subtract V. However, remember that there's one which is the overall one, which we might care or not depending on look at GTL or G, but there's certainly an overall momentum conservation delta function, as we saw, because of translation invariance. Right? So not all of these V's are independent, all of these V constraints are independent. One is the overall one, so I have to add 1. Okay? This is the number of loops. However, this contains the number of internal lines, and that's not something that's defined from the outside. From the outside, I define what? Well, I define the number of vertices, right? Because that's the order I'm looking at, right? I'm looking at order lambda to the V, means I have V vertices. And I define the number of external lines, which amounts to the order of the endpoint function. Now it's the eth point function, right? x1 up to xe. That's number of external lines, right? So these E and V are independent. The E and V are defined by what I'm looking at, but I is defined by the diagram. So I don't want this expression like this. I want it to be defined in terms of things I know beforehand, before drawing the diagram. So fortunately there's one more relation between these objects that allows us to rewrite this number of L. So we have to think of what happens to lines. So I have V vertices. So this is an example of a vertex that has, each one has P lines, and then out of each external point, external line, comes only one line, right? Okay. So now when I count, so let me count what happens to all of these lines coming from vertices. So I have V vertices, each with P lines. So a total of P times V lines. So what can happen to these things, right? Two things can happen. They can be connected with an external line. So E of these are connections to external lines. And the other thing that can happen is to be connected either like this or with another vertex. So in other words, being internal lines. But if they are internal lines, you see, I connect 2 points in an internal line. So this is 2 times I, right? So all in all, I get P dot V is E plus 2I. Okay, so now I can replace in here, get rid of I. So I is equal to PV minus E over 2. So L is, so V times P over 2 minus 1 minus E over 2 plus 1. Okay? And this is the number of loops of a diagram. So now it depends on things I know before drawing the diagram. Number of external lines and number of vertices.
This is only for fully connected diagrams. Can I have a different number of loops?
Yeah. Sure. But remember, sure. Yeah. Okay. But the point is, we haven't said that, but the point is, if I look at, so what interests me is not, as I said at the beginning of the class, it's not really the transition amplitude with free external lines, but rather with free vacuum outside, but rather with the full vacuum outside, which amounts, like in the operator formalism, by dividing by the vacuum bubbles. So when I divide by the vacuum bubbles, I only get connected diagrams. So, yeah. Otherwise, you're right. Yeah, I can get disconnected one, but that's kind of, not interesting because if it's disconnected, I just draw them separately, right? I do this connected piece, and then separately I do some other connected piece. So for each one, I can do separately. Right? All right. Okay, so now we have all the ingredients to write down the Feynman diagrams, the Feynman rules in momentum space. All right, so draw all the Feynman rules. Draw all inequivalent Feynman diagrams. So label all external momenta P1, Pn, and introduce independent loop momenta L1 to LL for which I write the integration factors. And then, let's say, label propagator lines by Qi, or Qj, using loop momenta and momentum conservation. Okay. Then for an external line, we write delta of pi, 1 over pi squared plus n squared. For an internal line, it's going to be delta of qj and then for a vertex, as before, we have minus lambda p now, since we're considering only in equivalent diagrams. So calculate S and multiply result by 1 over S. And then sum over diagrams. Okay. So this is now the form of the Feynman rules in momentum space. So you could still use the old form with a momentum for each line if you're not comfortable with this. But in the end, it amounts to the same thing, because this just tells you, how to skip a step. Otherwise, you would have to do all the delta function integrations at vertices, and then you would arrive at this. Okay? All right. So this was about Feynman diagrams. And finally, the last thing to do today is to write the most general bosonic theory. The point being that until now I've considered this simplified case with lambda being phi to the p, with the potential being lambda phi to the p. But in principle, I can have bosonic theory with more fields and couplings between them defined arbitrarily. So let's see how to do that. So most general bosonic field theory. So we will consider fields phi p, where p stands for some set of indices of some kind. They could be even Lorentz indices, like for example the electromagnetism gauge field A mu. Right, but generically, let me call these phi p. So generic bosonic fields. Okay. And then some kinetic term, which I will denote 1/2 integral this phi p of x, phi q of x, and then the kinetic term I'll define to be 1/2 with 1/2 delta pq of x, well, delta minus 1 pq. Okay? So I write it like this. Technically speaking, I should have, considering the way I defined it before, I should have write it like this, written like this, meaning double integral. Delta function, delta minus 1 is considered as double product, but anyway, let's keep to this notation, which is more obvious. Now, it's important to note that I wrote delta minus 1 pq, which kind of assumes it is invertible. But that's not always the case. In particular, invertible means it has no zero modes, right? It has no zero eigenvectors. But it could be that it has, and in fact, in this important case of electromagnetism, there are zero modes, zero eigenvectors. And those actually correspond to the directions of gauge transformations. Okay? The point is, these things tell us that in fact the space is too big, right? I can choose the gauge A0 equal to 0, for instance, which means that out of these mu, at least one, A0, is not physical, and that's, if I put it to a 0, then I get obviously a 0 eigenvalue. So that means that from a priori, when I write the kinetic term for such a field, I could have these zero modes, and then I have to deal with them. I have to do something that takes us back to an invertible operator, to just physical degrees of freedom, right? And that thing, for gauge fields in particular, will be a whole story. But I assume that that story is done, and I've come to something like this, where this is invertible. So just to say, for gauge fields, one will consider gauge fixing, like A0 equal to 0. I just put this because it sounds simple. Things are not so simple. But, and then we'll do something. We'll see that we have to be introduced as a result of gauge fixing some new object called ghosts, which also will have some propagators. So anyway, will be a whole different story that we need to do. The point is, once that is done, we arrive at something with an invertible kinetic operator. Okay? All right, so if I have these things, then I also consider a generalized interaction term. Which connects a random combination of indices among these phi p's. So let me write it as SP1 to Pn integral dvx vp1 Pn phi p1 of x phi Pn of x. And now comes the further generalization, I said these are indices, but note that if they are Lorentz indices, then I have to also have Lorentz invariants. And depending on how many fields I have in here, could be that I can't find a way to write something Lorentz invariant without derivatives. So in principle, these things can contain derivatives as well. Okay? Simply because, well, I mean, sometimes it's not even necessary for Lorentz invariance, but in general, if let's say I have 3 fields with 1 vector index, the odd number of fields with 1 vector index, then obviously I cannot make a Lorentz invariance combination. And I need an extra derivative to make one. So this in principle can contain derivatives and other couplings. The point is then the vertex, in this case, so with this notation I can basically just follow through all that we've done until now. You can write a Vic theorem, all the things that we did, this class and previous 2 classes about path integral formalism. And then find that the vertex is really, so before it was minus lambda, so now it has to be minus and, well, some sort of form for V, but what kind of form? Well, specifically the form is, I have to integrate over I should say the vertex in momentum space. The reason I say in momentum space is because I said it could contain derivatives. And in momentum space, a derivative just becomes a opinion, so it's something easy enough to handle. If I would be in X space, it would be a little more complicated because a derivative would have to act on a delta function or something like that. So that's so the generality is a little bit less. I would have to work a little bit harder to define generality. But if I do in momentum space, I just say I do a Fourier transform. So write integral and this exponent, and then I have the derivatives, the functional derivative with respect to p1, pn, xn of this coupling term. So let's.
Position space integration by parts is enough, right?
I'm sorry?
Integration by parts is enough to remove the delta function.
Yeah. Okay, so let's check that that we get the right result for the case we had before. So let's say 5 to the 4th, lambda 4 factorial ddx 5 to the 4 of x, right? So in this case, there's no indices, right? So I write integral ddx1 ddx x4 e to the I k1 x1 plus k4 x4, and then d let's write like this, d4 phi x1 until phi x4, and s is this integral with minus lambda 4 factorial, with lambda 4 No, yeah, I had a minus, and then lambda 4 factorial. And then the integral dynamic variable, yeah, I can still call it x. And then phi 4 of x, right? So when I take the first derivative, when I take the first functional derivative, excuse me. When I take the first functional derivative, I remove this and I replace x with, let's say, x4. So I take this first. But then I remove one phi, so I get a factor of 4. So minus lambda 4 factorial. Then a factor of 4 from this, from derivative, and then integral dd x1 to dd x4, the exponential. Then I have d3, d phi x1, d phi x3, then phi 3 of x4, right? This is after doing one derivation. Then, now when I do derivations, I'll get delta functions, right? So I will get, say, delta of, I do the next one, I'll get delta of x3 minus x4, but then I have integral over, let's say, x4, right? So that only replaces x3 with x4 in the exponent, in here, right? And so on. So at the end, you see I get minus lambda 4. So when I take derivatives, I get another 3, a 2, and a 1. All in all, I get the 4 factorial. That cancels the 4 factorial, right? And out of the integrations, I will remove 3, and I'm left with the last one. But in the last one, I already put all the x's equal, right? Because of the delta functions when taking functional derivatives. So in the last one, I have just integral dd, let's say x1, and then e to the I x1 k1 plus k4. So this is just the so the result is minus lambda 4 times 2 pi d delta d k1 plus k4. Okay? So this is exactly the vertex that we had before. Minus lambda times the momentum delta function. Alright? So now we've checked that we checked that our prescription gives the right result in this case we had before. Now we're convinced that this is true in a more general case. Alright, that's everything I want to tell you today. Do you have any questions? Questions about anything? So remember, Wednesday at 10 a.m. exam. So if you have other questions, now's the time. Yeah.
Could you explain again how you get the final propagator from the beginning propagator?
Oh, yeah. So the Wick rotation, you mean?
Yeah.
Right. Okay. So so the Euclidean propagator, as we saw, was this one. Right? Oh, okay. But then we had So, yeah, so we could have written delta of P, delta of P is equal to 1 over P squared plus M squared. And then in here we had defined, so for x0 we wrote E minus IT Euclidean, and correspondingly for momentum P0 became plus I P4 Euclidean. Right, so that means that if I look in P0, right, I look at, so P0 meaning the energy in Minkowski space, right? The contour of integration for the Euclidean propagator, so this would include the integral dp4, right? But this integral dp4 can be understood as integral dp0 over some contour in complex p0 plane, right? So the contour, however, is this contour, right? Going up along the imaginary line, right? Whereas the contour in Minkowski space would have been integration over real P0, which is this one, right? So what I want to do is to rotate the contour from here to here. However, remember the problem was that when doing so, we obtained, so here the pole is at P4 squared plus P squared plus M squared is equal to 0. But this is minus P0 squared, right? So the pole is at P0 P0 is plus or minus square root of P squared plus M squared, which is defined plus or minus EP, right? This is plus EP, this is minus EP, the pole, okay? So if I would rotate the contour completely, I would hit this. But more precisely, what does rotating the contour mean? Well, it means considering the full complex contour, so this is CI, whereas this is CR, real. But considering the full contour C, which is defined as CI, united with minus C real, right? Which means I go like this. So I go like this, like this, like this, right? So, by the residue theorem, well, assuming I can put this to 0, the integration here and here to 0, which works out, then the integral over C is 0 if there are no poles in C, right?
The part that I don't get is why the extra pieces go to 0.
Yeah, okay, so let's see. Well, I mean, all right, so this was... all right, let's see. So in this part, I would have IP4. So E plus IP4. Well, let me call this S. Or no, X. How did I call it? T, I call it, right? And this thing be P, the same as P0, X0. No, it should be, no, if I put them up, it should be with minus, of course. And the whole thing is minus I. And now I'm looking here for imaginary part P0 positive and real part P0 positive. Okay? And let's see if I get this right. So we had for X0 we had to put 1 minus I epsilon, right? Yeah, so now if I have real part of P0 positive, then X0 came with 1 minus I epsilon, so I have minus I and something positive times minus I epsilon. That gives a minus sign, right? So here, this will give E minus real part P0 epsilon times something else, right? So this vanishes here, right?
What is this 1 minus I?
The time, we had to put time going to 1 minus time times 1 minus I epsilon when considering the Feynman theorem for the propagator and so on. So that was one way of regularizing what the result that we're obtaining, was to put 1 minus I epsilon in time, right?
So that's for the contour, the horizontal contour, right?
No, but okay, but we can generalize this. The point is, we're doing a contour of a P0, but T is still T, right? Time is still the same, we're just bit rotating. Time bit rotates like this, so X0 bit rotates to T, right? But that's all. We don't move, in here we still consider the same TE and T0, right? And in this part, in here, I guess this other part. So in here we'll have imaginary P part P0 negative, and well, anyway, somehow this will also work out. I'm not getting myself confused right now, but again, this should work with another epsilon. Where does the other epsilon come from? Oh no, sorry. Yeah, no epsilon. The point is, now I have minus I times imaginary part negative, so another minus I, so this is minus times x0, right? So now it's negative just because of imaginary part p0 being negative, right? There's no epsilon needed here. So you need one epsilon in one of the two, but in this one it works without the epsilon. It works just because I have the I from the Fourier and the I from the imaginary part. And so I get this this decaying factor, right? So now to conclude, so these so these things vanish. So that means the integral of C being 0 because there are no poles, and this happens only if I do the rotation not to CR, but so I do the rotation with pi over 2 minus epsilon instead of the full pi over 2. And then that means that integral over C is 0, but integral over C was Ci united minus CR, and then with this C epsilons, the integral over the C epsilons vanishes, and so what I get is the integral over Ci is integral over CR. Okay, so the Wick rotation with pi over 2 minus epsilon gives the same result. Okay, so that means that delta is equal to delta Euclidean is equal to delta Feynman of the Wick rotation. All right.
I'm still not convinced that the extra piece is vanished, because it depends on the imaginary part of p0 that will give the real exponential that should kill it.
Mm-hmm.
Infinity. But if one side is positive, then the other, if one side is a negative exponential, the other would be positive.
Hmm. Yeah. Well, why was this? So here we've seen that it was the epsilon that makes this vanish. Yeah, no, normally there should have been the same epsilon that makes this vanish here as well, but why this is so? Yeah, this is not right. This doesn't work out. Now the point is anyway that momenta and time are conjugate, so they should transform in the same way. So
So this P0 will have an imaginary and real pair. So
no, but yeah, the point is Weak rotation should be considered, and it should be simultaneous in P and X because P and X are conjugate variables. Yeah, well, problem is here then. So here we established this because of the epsilon, but why is this also 0?
Maybe it's because on the bottom contour, the P0 is negative. So P0 will take care of the exponential decay.
No, that's what I said, but he pointed out that
And on one side, it will
yeah. So if that would be the case, this would blow up here, but it's not. The point is px should move, should be conjugate. No, but it's about. No, but the point is, there are 4 quadrants. Let's put it this way. There's 4 quadrants. And this thing would work, as we saw before, it would work in the upper half or lower half. But why is now, instead of upper half and lower half, is this and this quadrant and not this and this? I'm a little bit confused. Well, anyway, I'll think about it. I'll give you an answer next time. But anyway, this is not really relevant for, not useful for anything. It's just something that needs to be understood better. All right. Any other questions? All right. So I've corrected the exercises, but I didn't see any. I think most of you did things correctly. So